Thanks very much for the opportunity to talk to you about these results. The work I'm going to present is the result of a 5-year effort to construct this Go Green survey. What I've listed here is the core group of contributors. Is really a fantastic group of people to work with. Everybody on here has made substantial contributions to this work. I'm highlighting here with the photos the postdocs and grad students whose work I'll be highlighting today. So Go Green and GCLASS, which was an older survey based at somewhat lower redshift, were specifically designed to look at questions of galaxy evolution within clusters. And recognizing that there's a lot of influences on galaxy evolution besides environment, like the stellar mass, the redshift, the halo mass, the surveys were designed to try and control that parameter space to the extent we can, while still achieving a good statistically interesting sample. So Go Green spans a redshift between 1 and 1.5. The clusters are shown here on the diagram on the left, where I'm showing M500 as a function of lookback time or redshift compared to the SPT and ACT catalogs, just for comparison. And the lines are showing theoretical curves of growth for typical structures. So we span a wide range in halo mass, deliberately selected to be not the most massive clusters in the universe at that redshift, so that we're looking at the progenitors of things like Virgo and Coma today. We also span a wide range in stellar mass, and this requires very deep spectroscopy, which drives our exposure times. So for quiescent galaxies, we're reaching down to about 10 to the 10 solar masses in completeness over the redshift range, 0.8 to 1.5. All told, we have about 2,800 redshifts in the two surveys, and they nicely span all optical galaxy types, as we see here in the typical UVJ plane. Redshifts for quiescent galaxies down again to about 10 to the 10 solar masses. In addition to the spectroscopy, which was the foundation for the Go Green survey, we have 14-band coverage for most clusters at almost ultravista depths. So this is a nice comparison cluster sample, again, that can be directly compared with field surveys like ultravista. And so this is a typical cluster here, showing members and non-members identified spectroscopically for one of the clusters. For each one of these, we have wide photometry and the spectroscopy. And later today, Christy Webb will talk about fitting those things together. Here's just a quick list of our papers that have come out so far, and to highlight, again, Christy's talk coming up soon, and also poster A4 from Andrea Beffiano on the dynamics of clusters. I'm going to focus on mainly 3 of the papers here, 2 of them published and 1 just about to be submitted, and talk about how they relate to each other. So I'm going to start with the punchline. Effectively, I think the thing this was surprising a few years ago with GCLASS. It still sort of surprises me and makes me scratch my head a little bit. The main thing is that when we look at these clusters and we look at the fraction of quiescent galaxies in these clusters, they're elevated relative to the field at all stellar masses. And in fact, you can just see this looking at the nice color image here that Remco made. They basically look like low redshift clusters. They're full of quiescent galaxies. It's not maybe initially what you would expect, given how different the infalling galaxies are in terms of their star formation rates, their gas contents, how different the clusters are in terms of their masses, their presumably dynamical state of evolution. And so this ultimately is what I would like to understand, is why are these clusters already so evolved in their galaxy populations? So, we can see here also interesting that this difference between the cluster and the field, it looks sort of mass independent. And we can characterize this with this quenched fraction excess, which is the difference between the cluster and field quenched fraction divided by the fraction of star-forming field galaxies. This is this nice result from Yingji Peng et al. In 2012, showing that for satellite galaxies in dense environments in the local universe, this quantity is mostly independent of stellar mass. That's the purple line on the right. And our results are the black and the gray points there from Remco's paper last year, again, showing largely a mass-independent quench fraction excess, with maybe something different happening at the highest masses where we see even higher quench fraction excesses. But it's surprising that the number is the same to me. We're looking quite a ways back in redshift, and yet things look more or less identical to low redshift clusters. So why is that? So how can you get an excess of quenched galaxies in the cluster? Okay, in the field, there's all kinds of things that can quench galaxies, AGN, supernova feedback, all of that. But over and above that, why would you get more quenched galaxies in clusters? So you can have quenching of infalling field galaxies, okay, through things like ramp pressure stripping or tidal effects. You can have pre-processing, which is just that the quenching happened in dense environments before reaching the cluster. Or it could be something primordial, by which I really mean sort of enhanced self-quenching mechanisms that happen, let's say, in the protocluster environment over and above what happens to something in a non-protocluster environment. And these different scenarios will have different consequences for observables, like the stellar mass function shapes, any dependence on other sorts of environment, transition galaxies, and stellar ages. And that's what I'm going to try to tie together for you now. So first, the stellar mass functions. This is this nice paper by Remco last year. And I think, the surprising result was this shown on the left here. If we look at the stellar mass function for these quiescent galaxies in the clusters, compare them to the field, they're identical to a pretty high degree of precision, all the way down to 10 to the 9.5. This is based on the photometric sample calibrated by spectroscopic redshifts, which is why we can go down to those masses. This is not what we see in the local universe, okay, where on the right here, I'm showing a plot by Baldry et al. Peng showed the same thing, that as you look at quiescent galaxies in high density environments, you see a dramatic change in the faint-end slope of the stellar mass function, which they showed can be completely attributed to the quenching of infalling field galaxies. That doesn't work at all at low redshift, okay? If you tried to explain the excess quenching through the quenching of things that have a mass function like the star-forming galaxies, you can't maintain this exquisite shape. So that's really quite a puzzle, very hard to understand, actually. We can also look at the halo mass dependence, okay? So we have this wide range in halo mass from groups all the way up to the most massive clusters. And if we look at this, somewhat complicated plot here, but this is, again, this quench fraction excess as a function of stellar mass. The gray points are the ones I just showed you from Remco's work. And then the red shaded region here is the result from the low mass system groups that was done by my student, Andrew Reeves. This work has been submitted. What we see is a strong dependence on the stellar mass, in the sense that at low stellar masses, effectively we see little or no quench excess in the groups. But at the high stellar masses, we see as big an excess as we see in the clusters. Okay, so it suggests that the massive galaxies have already been quenched within low mass halos like groups, suggesting that pre-processing is important for these galaxies. But for low mass galaxies, it looks like most of this excess might be related to massive halos and are not there in low mass clusters. Okay, and I think Stephanie Werner is going to give a nice talk coming up soon, where she'll say more about this. That's interesting. The third piece of evidence I want to put out here is that we can look at transition galaxies. Okay, if we want to try to figure out how many galaxies are actually being transformed by their environment right now in the high mass cluster halo, we can look for transition galaxies. And we look at three different types in this nice paper by Karen McNabb, my master's student. This is just about to be submitted, hopefully this week or next week. We can look at galaxies in the Green Valley, looking at near UV minus V colors on the y-axis here. So we get a nice separation between the quiescent and star-forming population. Nice thing about the Green Valleys, we've defined it here, is every galaxy transitioning from the blue cloud to the red sequence has to pass through this. It doesn't matter what way they do it, whether it's fast quenching or slow quenching, they have to go through the Green Valley. Okay, but there's also all kinds of other ways you can end up in the Green Valley. Okay, so there's pros and cons. Another definition of these, what we're calling blue quiescent galaxies. So these are things in the box at the blue end of the quiescent sequence. This has been shown by several authors, including Bally et al. In 2019. contains primarily galaxies that are going through this fast quenching mode. Okay, so they're primarily coming through in this direction. And thirdly, there's spectroscopic post-starbursts. Thanks, Remco. Traditionally found via identification of strong Balmer absorption lines. That's what's shown in the purple here. So we can identify these from our spectra. And just to show here, actually, our Green Valley and our BQG population actually have stacked spectra that look quite a lot like these spectroscopic post-starbursts. Okay, so these are three independent different ways of looking at these transition galaxies. I'm going to show you just a few, I think, interesting results. First of all, if we look at the stellar mass function for these blue quiescent galaxies, it looks a lot like the stellar mass function of the star-forming galaxies. Okay, we can see here from the M-star alpha plot, the parameters are consistent with the star-forming galaxies, not the quiescent galaxies. So they're fully consistent with what you would expect for an infalling population of star-forming galaxies that has been quenched. We see an excess of these galaxies in the clusters at low stellar masses. Now, this is a little bit complicated. I just want to show you the punchline here, which is we can take this excess of post-starburst or transition galaxies in the cluster relative to the field, and under some assumptions, turn this into a quenching rate. And that's what I'm showing here in this figure. This is the rate, the fraction of infalling star-forming galaxies quenched per billion years as a function of stellar mass. We see consistent results looking at the BQGs, the post-starburst galaxies, and also the Green Valley galaxies not shown on here. With this mass dependence again, that at low masses, we're seeing a significant excess of these things in the cluster, indicating that there is a quenching of infalling galaxies. And at high stellar masses, we effectively see none. Now the errors are large, so we're also consistent with some infalling quenching, but we're consistent with none. Okay. And the last sort of plot I want to show here of this is that we can then compare this rate of quenching that we infer from the abundances of these galaxies. And again, they're all sort of consistent, these three different methods, with lower redshift measurements of post-starburst galaxies. And the uncertainties are large, and there's systematics we have to worry about a little bit as well. But just to show that these are consistent with a mild evolution of the quenching rate. And it's actually what you would expect. This green dotted line is what you would expect for a constant quenched fraction excess of 40%. Okay, if that's going to be constant, then you actually have to have an accretion rate which is evolving with time, again under some simple assumptions, and that time evolution is given by this green curve. So in other words, the fraction of transition galaxies we see in these clusters is consistent with the observation we have of a constant quench fraction excess with redshift. Okay, and I see the fireworks going, so I'm going to leave you with my conclusions. That I think what we're seeing here is that the higher stellar mass quenched galaxies very likely predate the cluster. Okay, they were pre-processed in groups or filaments or the infall regions. We're going to hear about that from Stephanie soon. Christy is going to talk about how she's measured ages for these galaxies. And it suggests that they're quite old. Their star formation stopped at high redshift. And so we would predict that there should be an excess abundance of quenched galaxies in protoclusters at redshift 2 to 3. At lower stellar masses, we seem to see evidence for accretion-based quenching within the high mass clusters themselves. And all our data was publicly released last year. You can get it from this website, and I'll stop here. Thank you.